let me know if you have any difficulty in listening, or if you have any difficulty in seeing the screen. Okay, so we'll start with. Right. So we know that a sinusoidal signal can be represented as a cos 2 pi fct or a cos omega ct, right? Or it can be simply written as a cos theta of t, right? So a cos theta of t, if you write a sinusoidal signal like this, so what it is a phasor, right? It is a phasor with amplitude of length of a. So you know complex numbers. It is nothing but um, this can also be written as real of a e power j theta t, right? So in amplitude modulation, what we have seen is we have varied the. Okay, let me write this as AC. Okay, we have varied amplitude of the high frequency signal. So AC cos 2 pi fct was the carrier, and we varied the amplitude of the carrier signal in accordance with the baseband signal, or M of t, or M of t is also called baseband signal or the message signal. Whereas in angle modulation, we vary the angle of the carrier, which is here theta of t, in accordance with the baseband signal M of t, right? So that's what we are going to study. And you know here WC is called the angular velocity. So okay, so this means AC is, it's a phasor with length AC, and it keeps rotating, say for example. So this length is AC, this length is AC, and if the phase theta is not changing with time, that phase angle theta is counterclockwise from the real axis, from the x-axis. So this is AC cos theta, right? This arrow represents AC cos theta, or yeah AC power j theta, and then it when it rotates with angular velocity WC. So WC is angular velocity. Say what angle modulation is: AC cos omega ct plus, what notation should we use? Should we use theta of t? Yeah, should we use theta of t? Right. So when theta of t is changed according to m of t, what is m of t? M of t is the baseband signal or the information signal. Baseband signal. Then AC cos omega ct plus theta of t is said to be angle modulated. Okay. So in angle modulation, there are like you will better understand when we exactly define what is a frequency modulation and what is a phase modulation, which we are going to do in the next one in the very next. Okay. So angle modulation can be thought of as two things. One is okay. One more thing we have to define before we do this is in AC cos theta of t. If we do differentiation of d theta of t divided by dt divided by pi 2 pi, this is frequency. Okay, we'll see this, right? Or in other words, in other words, okay. So two types of angle modulation that we discuss in our course is one is phase modulation. Frequency modulation. Okay. So if we define what is phase modulation and what is frequency modulation, you will be able to better understand the description in the last page, which we did, right? So in phase modulation, phase of the carrier signal with m of t. Okay, so let's consider the carrier signal AC cos theta of t. Okay, so this theta of t is varied 2 pi fct plus kp into m of t. Okay, so we know that carrier is AC cos theta of t, or when there is no modulation, it is AC cos 2 pi fct. Modulated carrier AC is AC cos 2 pi fct, but when we do phase modulation, its phase angle, this theta of t is varied as kp into m of t. This kp is some constant. We'll define it shortly. So this kp is called the sensitivity of the modulator. It is measured in radians per volts. Okay. So just note down this. So in phase modulation, the phase of the unmodulated carrier is changed linearly with respect to the baseband signal m of t, right? 2 pi fct is called angle of the unmodulated carrier M of t is the baseband signal and Kp is called sensitivity of the phase modulator measured in radians per volt. So this baseband signal is assumed to be in volts. It is assumed to be a voltage signal. It is assumed to be voltage signal. That's why this Kp is radians per volt, right? So phase modulated signal AC cos 2 pi fct plus Kp into m of t, right? So have you got convinced that the phase of the carrier signal is being changed in accordance with the baseband signal m of t, right? So this Kp is just some constant, like it tells you how much the phase should change in accordance with m of t. If Kp is very high, maybe maybe very high value, then the phase changes very abruptly, like the phase changes by a very high value, even if the modulating signal is very few volts. And if Kp is very low, then even if m of t is changed by a large number of volts, this phase won't change that much. So Kp is just some sensitivity parameter of the modulator. It is just some constant. So this is the phase modulator. As you know, the phase of the carrier signal is being changed in accordance with the baseband signal. So now the second type of the angle modulation is frequency modulation. Right? In frequency modulation, frequency of the carrier signal is varied linearly with the baseband signal m of t, right? So the instantaneous frequency fi of t is fc. See, the unmodulated carrier has got a fixed frequency fc, because we are considering a carrier AC cos 2 pi fct, right? So its frequency without any modulation is fc, but its frequency is being now varied in accordance with the baseband signal m of t. So this the instantaneous frequency of the carrier fi of t is into kf m of t. So this is called instantaneous frequency of the carrier, right? And fc is the frequency of the unmodulated carrier. Frequency of the unmodulated carrier. and m of t is baseband signal, assumed to be a voltage signal. And kf is the frequency, is the sensitivity of the modulator. It is radians per volt again. Sorry, it is hertz per volt because it's frequency. If for 1 volt change in the m of t, we want to change the frequency by say 10 hertz or 1 kilohertz or 10 kilohertz, then this kf should be in hertz. Sensitivity of the modulator. Right. Okay. So see, for phase modulation, we have got this expression, total expression, which is AC cos 2 pi f c t plus kpm of t. Whereas for frequency modulation, we have got expression for only the instantaneous frequency of the carrier wave. But we do want to write some expression like this, which is AC cos and so on, right? So let's do that, like so. Sorry. Okay. So we know that theta of t is 2 pi into 0 to t f of t dt. For any sinusoidal signal AC cos theta of t, this relation happens. So what do we have? We have f. Okay, this is instantaneous theta. This is instantaneous frequency. So this this what do we have? We have this equal to fc plus kf into m of t. So if I integrate this 0 to t fi of t dt is 2 pi into fct plus 2 pi into kf dt. Right. So this is this is nothing but theta I of t. So FM signal is given by AC cos 2 pi fct plus 2 pi into kf 0 to t m of t dt. Right. So you understood how you got it, how we got it. See, we have first defined the instantaneous frequency, and from frequency to angle, if you integrate out, yeah, if you integrate frequency from 0 to t dt and then multiply by 2 pi, you get theta. This is from your basic signals concept, right? So we have this fi of t, instantaneous frequency, is equal to fc into kf m of t. So this I am integrating it with respect to t from 0 to t. So it will be fct if I integrate this, and then multiplying with 2 pi. So 2 pi into fct. So this also into 2 pi, and when I integrate this will be 0 to t m of t dt, right? And what is our PM signal? PM signal is AC cos 2 pi fct plus kp m of t. So we have just defined what what is the frequency modulation and what is phase modulation. So this is FM signal and this is PM signal, right? Now based on these two equations, let us find out the relation between an FM and an AM signal. You carefully observe this. If I take m of t and then integrate out and then integrate that signal and then apply to a FM modulator, then I get a PM, phase modulation. Okay, so relation between PM and FM. What can you write here? Uh, if we take m of t, baseband signal, okay, and integrate it and integrate it to obtain 0 to t m of t dt, and then use that signal to generate a phase modulated signal result would be an FM signal. See, this might look confusing to you at the beginning, but just note down this sentence, then we will see. Okay. Okay. So that means what does this sentence says? We have the baseband signal m of t, right? Okay. So let's draw the diagram for this. We have baseband signal m of t, fine, and we have taken and we have integrated this signal. So let's give it to the integrator. And then here what do we get? 0 to t m of t dt. Okay, so if we take m of t and integrate it to obtain m of t dt, okay, we obtain integrated signal and then use that signal to generate a PM and then use this signal to generate phase modulator. So this phase modulator requires also a carrier signal, right? So let me write that carrier signal. So we have taken m of t, we have integrated that to get 0 to integral 0 to t m of t dt, and then this signal we are using to generate a phase modulator. Then what I am saying is that the result would be an FM signal. So is this correct? This is what this sentence, the above sentence says. Okay. So when I do phase modulation, so let me write that. A phase modulator is something like this: AC cos 2 pi FCT plus Kp into here. What do we have here? The baseband signal, right? See, in this bracket, we will have the baseband signal m of t. But in the above diagram, we are using the modulating signal as as the integral of m of t. So here I should use not m of t, but right. But this is nothing but your frequency modulated signal. Right? So you understood, right? Like if I don't have this integrator, if I don't have this integrator, if I don't have this integrator, then in this here I should write only m of t dt. In this case, it should be m of t, and it would be, because it's a phase modulator, it would be a phase modulated signal. But because I'm first integrating the signal, and then here I should write 0 to integral 0 to t m of t dt, it becomes a phase modulated signal. So I can produce an FM signal using a phase modulator, right? Yeah, so this concept is pretty simple, but just spend 2 more minutes on this, on understanding this. So yeah, I have a baseband signal m of t modulator. I first integrate that with respect to t, and then apply that to a phase modulator. Then the result will be a frequency modulator, because here in phase modulation equation, AC cos 2 pi FCT plus Kp into m of t, but here I am not modulating with respect to m of t, I am modulating with respect to integral of m of t. That's why I should write integral 0 to t m of t dt, and hence this becomes a a frequency modulated signal, right? Thus we can generate an FM signal using a phase modulator. Similarly, if we take m of t, differentiate the signal, and then use the differential of m of t to generate an FM signal phase modulated signal. So what I'm saying here, say we have m of t, and this we are differentiating it, right? So we are differentiating it and then applying it to a frequency modulator. And then this output, what I'm saying is, so here we have d by dt of m of t here, right? And then this output is a phase modulated wave, right? So how do we justify this? AC cos 2 pi fct plus 2 pi kf integral 0 to t m of t dt is the FM modulator equation. This is what an FM modulator does. So if you give m of t, an FM modulator, in place of this, in place of m of t, what I am substituting is d by dt of m of t. So this differentiation and this integration gets cancelled, and what do we get is AC cos 2 pi fct plus some constant k in, sorry, m of t, which is a PM signal, right? So you can generate a phase modulated signal using a frequency modulator. All that you need to do is take the baseband signal, differentiate it out, and then apply it to a frequency modulator. Similarly, you can apply you can obtain a frequency modulator using using a phase modulator, right? So you should understand these two relations thoroughly. So this part I just did it little bit fast, this part, so you understand it, okay? So this is a regular frequency modulator. If you apply m of t as the input to the frequency modulator, but instead of applying m of t, we have applied d by dt of m of t. So this differential and this integral gets cancelled, and finally you get this, which is nothing but the phase modulated signal, right? Yeah. So this means that we can, if we know the phase modulated signal, we can obtain the frequency modulation, and if we know frequency modulated signal, we can obtain the phase modulated signal. So this property holds good. So let me write. Signal can be deduced from PM signal and vice versa. Hence, we focus only on analyzing FM signal. Right? You understood the difference. Why do we focus only on FM signal is we know that both can be transformed from one equation to another equation. So if we can analyze one of these two signals thoroughly, we can also understand how the other signal behaves. So from now onwards, we focus only on the frequency modulated signal, right? So and another important remark is this. In FM and PM signals, the amplitude of the modulated wave remains constant. Is that right? See, if you recall those equations, the AC cos 2 pi fct, so that AC is remaining constant. So the amplitude is not changing with time. So the amplitude is constant. Whereas in amplitude modulated signals, the amplitude changes with time. One point, and the second point is the locations of zero crossings are not at regular intervals. That meaning in amplitude modulation, though the amplitude changes, we know that the frequency remains constant, right? So the frequency remains constant in the sense, so this is zero crossing. So these zero crossings happen at regular intervals. If the distance between these two is t seconds, the distance between these two is also t seconds, and so this distance between these two is also t seconds. But in frequency modulated wave, the frequency keep changing. So the frequency increases. So the zero crossings here are far apart in time. The zero crossing here are very close in time, right? So the zero crossings of the modulated signal are not at regular intervals. Hope you understood. Hope you understand this, right? Right, yeah. And the same thing happens true for phase modulated signals also. Yeah. So let's now discuss about a frequency modulated signal. Okay, so frequency modulated signal, as you can see, it's a non-linear function of the baseband signal. So, or I should write maybe, yeah, maybe baseband signal. Why? Because say FM signal f v of t is AC cos 2 pi fct plus 2 pi kf 0 to t, right? See this is called frequency modulated signal. This frequency modulated signal depends on m of t through its integral. So v of t depends on m of t through 0 to t m of t dt. V of t depends non-linearly on m of t. Okay, and that makes the analysis of frequency modulation difficult, right? So to start with, to have a gentle introduction to the analysis of frequency modulation, what we do is we consider single tone frequency modulation, right? What do I mean by single tone? Like we assume that the baseband signal is just one sinusoid. We assume, we consider the baseband signal to be modulated is just one sinusoid, which is am cos 2 pi fm of t, am cos 2 pi fmt, and then with that we modulate and then analyze the frequency modulation and then see its some of its properties. So single tone frequency modulation. So let's consider single tone frequency modulation. That meaning our m of t is a single frequency component. Am cos 2 pi fm of t. Then what is our frequency modulated signal? Is AC cos 2 pi fct plus 2 pi kf. Let me okay. So yeah, just wait for a second. Yeah, we'll go to this equation after 5 minutes. We need to see some more stuff before we go to that equation. Okay. So we know that now we are trying to do modulation with a single tone. So m of t is am cos 2 pi fmt, right? Then the instantaneous frequency of the FM signal is Fi of t is Fc plus Kf into Am cos 2 pi fmt, right? So we defined frequency modulation was we vary the frequency of the unmodulated carrier as Kf into m of t. So m of t here is Am cos 2 pi fmt. Am cos 2 pi fmt, right? Yeah. So now that means the instantaneous frequency of the frequency modulated carrier signal. So Fc is the unmodulated frequency. When there is no modulation, the frequency of the carrier is Fc, and then when there is a modulation, the frequency changes like this. And let's call this as delta F. Okay. So this delta F is called the frequency deviation. Okay, so you note, I hope you have noted it down, right? So let me wait for a few seconds so that yeah. So this delta F, which is Kf into Am, is called the frequency deviation. And as you can see, your instantaneous frequency of the FM wave is Fc plus delta F into cos 2 pi FM, right? As cos 2 pi FMT can take values between -1 and +1, your maximum frequency of the modulated signal is Fc plus delta F, right? Because when cos 2 pi FMT equal to 1, and similarly, what is minimum frequency of the modulated signal? Fc minus delta F, right? The maximum frequency is Fc plus delta F. The minimum frequency is Fc minus delta F of the modulated signal. Because cos 2 pi FMT can take values, maximum value of +1 and minimum value of -1. Note that the frequency deviation delta F is proportional to Am, right? Because delta F is Kf into Am. So what is Am? Magnitude of the Magnitude of the baseband signal. And you should also note that delta F is independent of FM. What is FM? Frequency of the baseband signal. Right. So now we have this Fi of t, and then so now we have this. Then how do you get theta I of t? Theta I of t is 2 pi into 0 to t Fi of t dt. So what is that? 2 pi into Fct plus 2 pi into delta F into sine 2 pi Fmt divided by 2 pi Fm. This 2 pi gets cancelled, right? So we have the instantaneous frequency. From that I want to get the angle of the signal. So that angle is obtained as integral of the instantaneous frequency multiplied by 2 pi. Integrate this out. So which is it and multiply by 2 pi. So it becomes 2 pi Fct plus 2 pi into delta F. So integral of cos 2 pi Fmt becomes sine 2 pi Fmt divided by 2 pi Fm. This 2 pi gets cancelled, and then here we have this. So let me rewrite this. Okay. So I'll wait for a few seconds so that you can note this down. You can note down this equation. Yep. Where are we? We are here. So theta I of t 2 pi Fct plus delta F by Fm into sine 2 pi Fmt. So let's call this as beta. Now the single tone modulated FM signal is given by AC cos theta I of t, that is equal to AC cos 2 pi Fct plus beta sine 2 pi Fmt. This is the equation of a single tone modulated FM signal. What is beta? Depending on value of beta, we classify FM into we classify the FM signals into narrowband FM and wideband FM, right? So we what did we get? We get the a single tone modulated FM signal equation is this. This is given by AC cos 2 pi FCT plus beta into sin 2 pi FMT, where beta is delta F by FM and delta F is KF into AM, right? And now, what is the importance of this beta is, if beta is very small, less than 1 radian, then we call it a narrowband FM, and when beta is very high, we call it a wideband FM. Okay. When beta is small, compared to 1 radian, we call it a narrowband FM. When beta is radian, we call it wideband FM. Okay, so that is the importance of the parameter beta. Okay, so I'll take another 10 minutes. We'll stop in another 10 minutes. Okay, so because we can complete this. So where are we? We are here. Yeah. Let's focus on narrowband FM. Right. So we are considering a single tone FM, which is AC cos 2 pi FCT sorry, again I did a mistake. Yeah. Yeah. So it is AC cos 2 pi FCT plus beta sin 2 pi FMT. cos of a plus b. So AC cos a cos b minus sin a sin b, right? Cos a cos b minus sin a sin b. Right here also let me sorry. Yeah, so I just wrote the singleton FM wave and then expanded it, and then we are considering a narrowband FM, right? Uh, for for narrowband FM, beta is small, right? When beta is small, what we can do is we focus on this thing and focus on this thing. So these two are terms containing beta. Okay. So cos of beta sine 2 pi fmt. This approximately this becomes 1, and then sine of beta sine 2 pi fmt. See, when theta is small, sine theta is approximately equivalent to theta. Sine 2 pi fmt. Cos theta, when theta is small, it is almost equal to 1, and sine theta, when theta is small, it is equivalent to theta, right? So we use these two approximations and then write our v of t as, see, now v of t is approximately equal to AC cos 2 pi fct into, in place of cos of beta sine 2 pi fmt, we put only 1, right? So there is into 1 I'll put minus AC sine 2 pi fct into, in place of this I'll put only beta sine 2 pi fmt, right? So this I can write this as AC cos 2 pi fct minus beta AC into sine 2 pi fct into sine 2 pi fmt. Is that okay? Yes. So now let's expand this. This is sin A sin B formula, right? So sin A sin B, and of course there is a negative sign. So this can be written as AC cos 2 pi fct So now I'm trying to make use of sin A sin B formula, but here I will put place. So beta AC by 2. So beta AC by 2 cos 2 pi FC plus FM cos 2 pi FC plus FMT minus cos 2 pi FC minus FMT. Yeah. So you can verify this. So this is here I simply apply sin A sin B, which is equal to cos of A minus B minus cos of A plus B. So there is this minus sign in front of this equation. So that minus and inside minus, yeah, it finally you get this. Okay. Yes. So what do you have here? You have this. You have the carrier signal AC cos 2 pi FCT, and you have cos 2 pi FC plus FM. Hey, it looks somewhat familiar, right? It is kind of upper sideband signal in in an amplitude modulated wave. And then there is cos 2 pi FC minus FM, which is a lower sideband signal in an amplitude modulated wave, right? So this is equivalent to, there is a carrier component, there is FC plus FM, an upper sideband signal, there is FC minus FM, a lower sideband signal. Of course, this sign is negative here. Okay, so let me, so just first you note down and then compare this with an AM signal. An AM signal meaning double sideband with carrier signal. Right. So what do we have here? Okay, we have it here. So let's note this down. Yeah, and then compare with an AM signal. This FM signal equation looks similar to that of an AM signal equation. So what is an AM signal equation with double sideband, that meaning DSB C signal, AC cos 2 pi FCT plus some constant into cos 2 pi FC plus FM of t plus cos 2 pi FC minus FM of t, right? So what this is FC, this is FC plus FM, this is FC minus FM, right? So this is the double sideband with carrier signal. You have the carrier, you have FC plus FM, which is upper sideband signal. When the modulating signal is only single sinusoid, and you have FC minus FM. So the total bandwidth of this spectrum is 2 FM, right? Because the signal is occupying from Fc minus Fm to Fc plus Fm. Similarly, on the negative thing, you have you have minus Fc, you have minus Fc minus Fm, you have minus Fc plus Fm. You have a peak here, you have a peak here. Now, Fm signal has same equation as that of AM signal, except for the sign change for cos 2 pi Fc minus Fm temp. Right? So let me explain to you what do I mean. Okay. So let me go back to this equation. So in this equation, we have seen that there is AC cos 2 pi Fct, there is cos 2 pi Fc plus Fm, there is cos 2 pi Fc minus Fm. But for the cos 2 pi Fc minus Fm, there is a negative sign here, right? Okay, there is a negative sign here. And for an AM signal, there is AC cos 2 pi Fct, there is cos 2 pi Fc plus Fm, and there is cos 2 pi Fc minus Fm, but here this is a positive sign. So except for this sign change, the narrowband FM equation with single tone modulation is very similar to the double sideband with carrier modulated AM modulation. And we know that the bandwidth of the AM signal is 2 FM. So the bandwidth of FM signal is also equivalent to 2 FM. Right? So this shows that the bandwidth of narrowband FM with single tone modulation is equal to 2 into FM. Yeah, please note down. Then I'll explain to you just one more time, just for 2 minutes, and then we'll stop this class. Like, yeah. Right? In other words, to summarize, the narrowband FM signal with single tone modulation. So single tone modulation meaning what? M of t is equal to AM cos 2 pi fmt is given by V of t is equal to AC cos 2 pi fct plus beta AC by 2 cos 2 pi fc plus fmt plus cos 2 pi fc minus fmt. Sorry, here it should not be plus, it should be minus. The spectrum of the above signal has frequency components at fc, fc plus fm and fc minus fm. See, simply you need not even compare this with the AM signal. If you just look at this signal and then see its frequency, if you think about its Fourier spectrum, if you think about it, see this is the time domain signal. So this is the narrowband FM signal with single tone modulation expressed in the time domain. So if you interpret this in the frequency domain, you have a frequency component at Fc because of this term. You have a frequency component at Fc plus Fm because of this term, and you have a frequency component at Fc minus Fm because of this term. So that's why the bandwidth, it has got components at these frequencies at Fc, Fc plus Fm and Fc minus Fm frequencies. And the bandwidth of the signal, because we have useful component at Fc minus Fm and another component at Fc plus Fm. That means the bandwidth of the signal is 2 into Fm. Thus, the bandwidth of a narrowband FM is twice the bandwidth of the baseband signal, right? So that sort of completes our discussion of narrowband FM signal.